In this example, we want to find a singular value decomposition for the 2x3 matrix A. Okay, first thing that we want to decide is, are we going to find the singular values for A transpose or A transpose A? In this example, it might be easier to start with A transpose. Because we've got a 2x3 matrix, we'll end up with a 2x3 times a 3x2, which gives us a 2x2. And so when you multiply these matrices together, we get 3, 2, 2, 3, 2, negative 2. Uh, 3, 2, 2, 2, 3, negative 2 gives us a matrix 9 plus 4 plus 4 is 17. And then we've got 6 plus 6 minus 4 is 8. And then we've got 6 plus 6 minus 4 is 8. Then we've got 4 plus 9 minus 4. 4 plus 9 plus 4 gives us 17. Okay, and because we've gone A transpose rather than A transpose A, gives us a 2x2 rather than a 3x3 to work with. So our eigenvalues we get from the determinant of A minus lambda I. So that's the term of 17 minus lambda, 8, 8, and 17 minus lambda. So we have 17 minus lambda squared minus 64. And we multiply that out, collect like terms, and factor away. And we end up with lambda minus 25 and lambda minus 9 equals 0, which means lambda is going to be 25 or 9. So those are our two eigenvalues. And so our singular values, sigma 1 is root 25 or 5. Sigma 2 is root 9 or 3. So this gives us right away our singular value matrix. The singular value matrix has the same dimensions as the original, with the with the singular values down the main diagonal. Good. Next, we want to compute the eigenvalues. The eigenvectors, I should say. So for lambda equals 25, we end up with the matrix 17 minus 25 is minus 8, then positive 8, then 8, and then 17 minus 25 is minus 8. And so we end up with the eigenvector x, the equation x equals y, or the eigenvector 1, 1. Now we need to normalize that, so let's multiply that by 1 over root 2. Next, lambda equals 9. So our matrix here is 17 minus 9 is going to be 8, and then 8, then 8, and then 17 minus 9 is again 8. This is x is equal to negative y. And so when we normalize, we get 1 over root 2, negative 1, 1. Great. Now, we have to be a bit careful because we looked at AA transpose. This is we're making our U matrix. 1 over root 2, 1 over root 2, this eigenvector, and then negative 1 over root 2, 1 over root 2, this eigenvector. Now we need to deal with our right singular vectors, our V column. So V1 is going to be 1 over 5, 1 over sigma 1 times A transpose times U1. So 1 over 5 times 3, 2, 2, 2, 3, negative 2 times U. And U1 is that 1 over root 2, 1 over root 2. That first eigenvector. Okay, so I'm confident that we're going to end up with a 1 over root 2 out front. We might end up with a multiple of 5 as well. So I'll pull the 1 over root 2 out front. We end up with 3 plus 2 is 5. Divided by 5 gives us 1. 2 plus 3 is 5. Divided by 5 gives us 1. 2 minus 2 is 0. So that's our vector V1. Our vector V2 is 1 over sigma 2, A transpose U2. So this is 1 over 3 times 3, 2, 2, 2, 3, negative 2 times negative 1 over root 2, 1 over root 2. So we'll end up with a 1 over root 2 out front. And we end up with minus 3 plus 2 is 1 divided by 3. I'll pull the 3 out front here. So it's just 1. And then we've got minus 2 plus 3 is positive 1. Then minus 2 minus another 2 is minus 4. So that worked out much better pulling the 3 out front. So minus 3 plus 2, that's a minus 1 out front there too. Okay. We need to find a third vector, V3, that's orthogonal to V1 and V2. So one that we might try is minus 2/3, 2/3, and 1/3. Okay, and conveniently, that's unit length. If we use this, that'll give us a third unit vector, and we can see that it's orthogonal to both of our first two vectors. Okay, so this gives us our V. Our V is going to be 1/√2, 1/√2, 0. Our next one is -1/3√2, 1/3√2, and -4/3√2. And then -2/3, 2/3, and 1/3. And indeed, if you multiply these vectors together, these matrices together, you're going to find that A is equal to U sigma times V transpose.